Welcome to Unit 7, Inference for Quantitative Data with an emphasis on means. This is a follow-up video to topic 7.2, constructing a confidence interval for a population mean. We're going to look at some examples. All right, hopefully you watched the video on how to do all this first, because it's actually really easy. Let's look at two good problems, and they actually have a little bit of a difference that I think it's important for you to see. All right, example 1. What is the mean amount of time a name brand AAA battery lasts? My goodness, I have no idea. Well, to find out, Becky selects a random sample of 55 name brand AAA batteries and runs them each in the flashlight until the flashlight no longer operates. That way she can record the time each of the 55 batteries lasted, and then she uses all those times to calculate the mean and the standard deviation of her sample. So she has 55 different times, and she's going to more than likely plug all that data into her calculator or some type of computer software to get the mean and the standard deviation of her sample. Now, the mean was 348.7 minutes, and the standard deviation was 23.8 minutes. So remember, this is the mean of her sample, and this is a point estimate. We're hoping that this points us towards the mean, and the standard deviation of our sample was 23.8 minutes. Now, we are instructed to construct a 99% confidence interval for the population mean amount of minutes a name brand battery lasts. So essentially, we're going to take her mean, we're going to go up and we're going to go down by a margin of error. And the idea is that, what do we mean by 99% confident, right? Well, we're going to envision that sampling distribution. And we're going to envision that, 99% only puts 0.5% at the bottom, 0.5% at the top. So we're very, very, very confident that even though we don't know the true mean in the middle, we're very confident that Becky's sample is going to be somewhere in that middle 99%, where when she creates an interval around it, she'll capture the true mean in it. All right, so we're going to need a t-star, and we're going to need our standard error, which is s divided by the square root of n. To be honest, guys, we already have everything we need. We know the sample mean, we know the sample standard deviation, we know the sample size. The only thing we're going to have to quickly find is the t-star, which we'll do in a moment. But we do have to run through the 4 official steps. Step 1 is naming what you're doing and putting a little bit of context. This is a 1 sample t interval for the mean amount of time in minutes that all name brand AAA batteries will last in this mentioned flashlight. Now, notice the part I underline is like, the official name. This is a 1 sample t interval for a mean, and then we got to give that context. It's the mean amount of time that batteries are going to last in this flashlight. All right, step 2 is really thinking about the sampling distribution. Well, 2 comments here. First off, the sampling distribution is going to follow a t model. Why? Because I'm using s divided by the square root of n for my standard error. So instead of using sigma, I'm replacing it with s, and that's why we have to use a t model. So the good news is the conditions sound very familiar for that t distribution. First, the sample 55 batteries was randomly selected to avoid bias. I got to assume that 55 name brand batteries is assumed less than 10% of all name brand batteries to assume independence. And finally, we do not know what the population looks like for all batteries. It never said it was normal or not. Who knows? Could be skewed, right? I mean, if you think about it, I guess this is kind of a waste of time. But real quick, if you think about it, the battery company's probably hoping that it's skewed to the right. They probably hope, excuse me, that there's not a ton of very long batteries, but most are in some particular value. Whereas you probably hope it's actually skewed right, where a ton of batteries last a long time. But regardless, the point I'm trying to make is we don't know what the population looks like. But wait a minute, doesn't matter. Our sample size at 55 is larger than 30, so it's safe to use the t-distribution. We know that the t-distribution is not going to be skewed by any means, even if the population is. Because our sample size is over 30, 55 is, we know that we can use a t-distribution that looks pretty darn normal. All right, step 3 is going ahead and actually building the interval. This is like the easy part. So I'm going to take Becky's mean, 348.7 minutes. I'm going to go up and I'm going to go down. Let's talk about the back part first. Her standard deviation of her sample was 23.8 minutes, and the sample size was 55. All right, so where did I get the t-star from? Well, let's just briefly go over this. I'm going to do second vars on my TI-84 calculator, and I'm going to find invert t right underneath invert norm. This is where you get special t-stars. So 99% confident, the area at the bottom is the area that the calculator is asking for, and that's 0.005. The area at the bottom is only 0.5%. And then again, this is a very specific t model with 54 degrees of freedom, because the degrees of freedom is just your sample size minus 1. All right, so that gives us our, takes a second, there it is, 2.66998. And you can see that I did round that to 4 decimals, 2.6700. Please note that it's negative because you only looked at the bottom. That's what the calculator does. The top would be positive 2.67. But remember, that positive and that negative is taken into account right here with the plus or minus. All right, so once you calculate your margin of error, for me it was about 8.569 minutes. So again, here's what I'm saying. I'm saying pretty confident that, my mean, 348.7, is pretty close to the true mean. That way, if I go up and I go down by about 8.5 minutes, I'm pretty confident that I'm going to capture the truth. So the interval is 340.13 to 357.27 if you do a little bit more rounding there. All right, so now it's time for my conclusion. Pretty easy. I'm 99% confident that the population mean time that a name brand AAA battery will last in the flashlight mentioned is between 340.13 minutes and 357.27 minutes. Just a couple comments. The reason why I keep saying the flashlight mentioned is because other devices might potentially waste more battery, and a toy might die sooner, or maybe something small that doesn't use a lot of power might last longer. So I have to keep mentioning this is in the flashlights that she used. All right, also please make sure that when you conclude this, you're not talking about your sample mean. We know the sample mean. You're talking about the population mean. Intervals are trying to find the population mean. The sample mean's not up for question. Becky knows what the sample mean is. It was the 348 number. So again, a confidence interval is trying to locate the population mean. All right, pretty easy. Let's look at one more example. I want to show you how this one's actually a little bit different. Blood pressure. A doctor wanted to estimate the mean systolic blood pressure of teenage athletes while they are at rest. Sorry for the typo there. All right, he collected a random sample of 22 male athletes from around the country, and he measured their blood pressure while they are resting. The blood pressures in mmHg of each of the 22 male athletes are below. Construct a 95% confidence interval for the population mean blood pressure of all teenage male athletes. Okay, so we're searching for mu, the true mean systolic blood pressure of all teenage male athletes. And we're going to hope that our sample mean points us in that direction. Now, what's different about this problem than the previous problem was that I don't give you the mean of the sample. I just give you the data, which means you're going to have to find the mean on your own. And obviously, if I'm going to figure out the formula for this confidence interval, I need to find S as well. Now, you are more than welcome to use the formulas by hand to find the mean and the sample standard deviation, but trust me, you're not going to want to do that. So anytime the data is given to you, instead of like in the previous problem where the mean and standard deviation are given to you, you do have a little bit more work, but it's not very difficult at all. The first thing you have to do is go to your calculator, hit Stat, and then go to Edit and get this data typed into your calculator. So it doesn't matter the order you type it in, but all the data has to be there. I'd recommend triple checking that you type them all in right, because if you get one wrong, it's going to mess everything up. So go ahead and type in 110, 122, 115, 123, excuse me, gosh, can't read, 109, 120, 129, 105, 114, 118, 116, 99, 117, 118, 106, 111, 110, 129, 118, 115, 116, 111, 113. Get them all typed in there. And that's pretty much the extent of what you have to do. Then you're going to hit Stat. You're going to slide over to Calc, do one variable stats. Make sure you select the list you put it in. I put it in list 1. If you put it in, for example, list 2, you'd hit second number 2 to get list 2. Leave the frequency list blank. If you recall, we only put something there when there were probabilities attached to outcomes. That was back in our probability unit. So we're not dealing with that right now. So make sure the frequency list is left blank and hit calculate. And that's pretty much it. Bingo, there it is. 114.6363 is the mean. And the standard deviation is 7.1417. So, getting those two things is super important. I would definitely make sure I write those down. So 114.6363. The more decimals you keep, the better. I'd always recommend more decimals. Actually, that should be 0.6364. I'll change that in a second. And 7.1417. 7.1417. Now, again, honestly, if you want to use 3 decimals, that's totally okay. I would not do less than that. If you kept 2 decimals, is it going to be the end of the world? No, but just understand that the more decimals you keep, the more accurate you're going to be. All right, now that we got the information we needed, which didn't really take that long at all, now we're ready to go ahead and construct our interval. All right, first step is we're going to have to go ahead and name what we're doing. This is a 1 sample t interval for the mean systolic blood pressure for male teenage athletes while at rest. One more time, why are we using a t-interval here? Because we are replacing sigma in the formula for standard deviation of the sampling distribution with S, the standard deviation of our sample. That question might be popped up to you. All right, now to make sure that we could use that T model, even though, again, you got to understand the whole process here, and I know I've probably gone over it too many times, but you got to understand the whole process here is I want to envision the sampling distribution even though I'm going in blind. I don't know what the mean is, and I certainly don't know what the standard deviation is. Actually, I have to use standard error anyway. So that is why we're going to end up using a T model, which looks a lot like the normal model as I described in the previous video. All right, so I do have to make sure the sample 22 male athletes was selected randomly to avoid bias. I do have to make sure the sample 22 male athletes is, it's got to be less than 10% of all male athletes to assume independence. And finally, I need to make sure my sample is big enough. And this is where I actually run into a little bit of a problem. I'm not bigger than 30, so central limit theorem can't help me make sure that the T model is appropriate. And I also don't know what the population looks like. So this is something that does often happen, especially on the AP test. We have to actually check our data. Remember the concept. If your sample looks roughly normal-ish, roughly symmetric-ish, then that means the population probably was as well. So that's the situation where we could be okay. So we just have to check our data and make sure that there's no major skewness, no major outliers that would make us think that the population is skewed left, skewed right, or something really weird. So how do I do this? Well, I actually pulled up a graph right there for you, but you actually will need to do this on your own and draw a rough sketch. It doesn't have to be, the greatest sketch ever, but should be a rough sketch. Now, this is really easy to do on your TID4 calculator. First off, you already have the data into your calculator anyway. It's already there, so come on. That saves a little bit of time. Now we just have to make a histogram. Quickly, how do we make a histogram? Hit y equals. First and foremost, make sure you have no equations typed into y equals. Then we actually have to go to our stat plots, which is second y equals. Go to plot 1, turn it on. Then we're going to select a little histogram because we want to make a quick little histogram of our data just to make sure there's no major skewness or outliers. And the histogram is looks like a histogram. And then the only other thing we have to do is choose the list our data is in. Again, mine is in list 1. If you use list 2 or list 3 or list 4, then you would hit second L2, second L3, second L4 to get that. All right, once that's all done, you can go back to the home screen. And then the best way to zoom in on information you enter into the stat is if you hit zoom and then number 9. Zoom number 9 is our zoom stat feature, which will zoom in on your stats. And there it is. There's your picture. Now, if this was a AP test or a test in your class, then you might have to make a rough sketch of that just to prove that there's no major outliers or skewness. Now, listen, I'm not saying that that looks normal by any means. It's not bad, but it's not perfect. And that's okay. It's only 22 guys anyway. I mean, with a sample of 22, you're not going to get the greatest picture. So just understand you're looking for no major skewness, which you clearly don't see, and no major outliers. I use those words major because you might see an outlier that you think, well, that's kind of high, but is it major? Is it way to the right? I mean, is it 100 value points better or worse? You know what I'm saying? Those are major outliers. And then same thing with skewness. I mean, I need to see a direct tail only on one side. That would be major. I clearly do not see that here. So that is why it's still safe to use the T distribution with 21 degrees of freedom, even though I'm under 30 and I don't know what the population is. That's a pretty important step right there. That's why I took a little bit of time understanding that. All right, step 3, really easy. All right, I'm going to go ahead and take the mean of my sample. Remember that was 114.636. I'm going to go up and I'm going to go down by my margin of error. So I'm taking the standard deviation of my sample, 7.142, and I'm dividing it by the square root of my sample size. And then the only number I need right here is T star. Let's go over how to get T star one more time. So we're going to go second vars, go down to invert T. And again, we wanted a 95% confidence interval, so that puts 0.025 at the bottom, 2.5% at the bottom. And we have 21 degrees of freedom. Remember, there's a different T model for every sample size based on the degrees of freedom. And this gives us our special T star of 2.0796. So pretty easy, right? Then I want to show you this real quick as well. When you multiply that back part to get the margin of error, just do it all at once. 2.0796 times 7.142 divided by the square root of 22. The only issue some kids do every now and then is they put the entire back part in a square root. They kind of like confuse that with the standard deviation for proportions where the entire fraction is in square roots, not for means. So please make sure you use the formula properly. Hit enter, boom, there's the 3.1666 that we got. Okay, that's our margin of error, so I'm willing to say, listen, I know that my sample's not perfect. It's definitely not necessarily the truth, but if I go up a little bit and I go down a little bit, I'm pretty confident that I will capture the truth, because if you envision that sampling distribution, I'm pretty sure my sample is one of the ones near the center. So if you go up and down by the standard deviation, you get the 3.1667, and that's how I got the 111.469 to 117.803. Now it's time for my conclusion. I'm 95% confident that the population mean systolic blood pressure of all teenage male athletes is somewhere between 111.47 and 117.80. Now, remember, this is the mean of all. And you might say, well, my blood pressure is 119. Okay, you're just one person. That doesn't mean that you're weird or unusual. We're talking about the mean here. We're not talking about you or Tom or Doug. We're talking about the mean of all teenage male athletes. And that is why just because you're not in this doesn't mean that you yourself are weird, high or low. This is the mean of all teenage male athletes that we are 95% confident is in this interval. All right, guys, that's it for the example video. Hope the examples were incredibly easy and very easy for you to follow and understand.